Hello, my name is Wayne Messam II, and this demo reel showcases several procedural audio systems I've built across different games using Unreal Engine, MetaSounds, Wwise, and the Quartz music system. These systems leverage real-time gameplay data to dynamically drive music, sound effects, and other audio responses, resulting in soundscapes that feel alive, immersive, and deeply integrated with player actions. We'll begin with Crumble Party, a whimsical narrative board game where I built in an interactive music system and a sequential sound effects system that responds to a player-driven harvesting mechanic, all without middleware. During the early stages of development, I created the harvesting mechanic using a boolean in C++ to let the class know whether we are harvesting or not, because the player has total control over when the harvesting starts and stops. This is why I opted to utilize the event tick for calculating the time it takes to harvest a cake piece based on the items the player uses to upgrade their dig speed and the debuffs they accumulate along their journey around the board. The harvest bar variable refers to the amount of time left before the next cake piece is harvested. Regardless of the upgrades the player has received from items, the cake piece will always proc 5 times before falling. Each time we are spawning a sound at the location the harvest takes place and increases the pitch index of that specific cake slice by 1, so that the float parameter in the metasound adjusts accordingly as well. At the same time, the player harvesting metasound is playing for as long as the player is holding down the harvest button. Once we reach 5 procs of the cake piece being harvested, the cake piece itself then triggers an audio warning that increases in intensity via a timeline, with an alpha that increases the intensity of the audio warning metasound within a map range value between 0 and 1, with the minimum value being set to 0.5 and the maximum value set to 1 for the loop duration of the sound effect. After the timeline is done, the falling cake slice will trigger a metasound that activates an envelope and delay, reacting to a filtered pink noise output to simulate a fun falling effect. The interactive music is run by using Unreal Engine's Quartz system. I created an actor blueprint called Music Handler and placed it in the game world. The function of this actor is to interactively trigger new developments of the music based on the tile the player lands on. After setting up our quartz clock to 4/4 time and a BPM of 440, we call play BG music through the level blueprint. Quantize to the next bar when transitioning. This blueprint handles changing the music to the various tracks depending on the tile the player lands on. For example, when landing on the minigame tile, the track transitions into a more focused loop for players to prepare themselves for the coming minigame. This blueprint also holds functionality for transitioning to the diegetic PA system, playing the music across the town. We created a submix and a preset for the loudspeakers when we zoom out, by adjusting the envelope follower, the filter frequency, and the filter type. To zoom in, we just remove the effects, but the music remains playing in 2D. After the player returns to the board, the music skips the intro sequence of the track and jumps straight into the main track's loop through the level blueprint, using information from the game instance. It took constant testing to make sure all the tracks were working appropriately each playthrough of the game, exactly as we wanted them to across multiple sequential playthroughs. The music ultimately ends when the player runs out of turns, at which point they will either hear the good ending or the bad ending. Alright, next is Project EQ, a rhythm-based endless runner where my team and I designed a fully procedural music and scoring system using MetaSounds and Quartz. This system interprets metadata embedded in audio files to generate synchronized gameplay cues and musical feedback in the form of markers, letting players literally play and compose music through their actions. Dave, our composer and technical sound designer, will get us started on how the system fits into place.
So I'm going to show you here how the notes or the rings in Project EQ's levels work. Now here we are in Reaper. So you have the song. There's 3 parts to the song, and they're just exported out in their own sequences. Now you see these 3 different tracks with all these singular notes, and you'll notice that each note is tied to a different colored marker with a particular label on it. Because of the way Unreal Engine works, we can actually export the markers embedded into the WAV file. So when we export this file into Unreal Engine, it has all of these markers in it. The reason I have them separated by color is to make sure that we can tell which one is which. We have 3 different modes in the game. We have easy, medium, and hard mode. On easy mode, you'll see that there are less notes, or they represent themselves as rings in the game. In medium mode, we have a little bit more, and in hard mode, we have all of them. Reading through the different variables, we can, they're also, I'll go over these, there's also another set of markers here too. But through parsing the titles of each marker, we can tell Unreal Engine which markers are for which mode. So let's say if we're on easy mode, it's only going to read S0 markers. See that these S0 markers map right down to, where are they? They map right here. So you'll see every note in S0 is each note here. Same goes for medium markers. Here you'll see the S1, and here for S2. Where is it? There it is. S2. You'll see all these S2. And I'll quickly play you what these kind of sound like. I was just slightly out of time, but so in the actual game, you don't hear those sounds. I just have those sounds there so I have an audible cue of what these are. And the easier modes are just taken from this hard mode. So I would play the hard notes for the hard mode first, and then pull out notes for easy and medium. And so when you pick the hard mode in the game, Unreal Engine will read all of these markers. If you pick medium mode, it will ignore the S2 markers and only display things for S0 and S1. And if you pick easy mode, it only just shows rings for S0. Now, also, we have these markers here. You'll see the A minor here. I'm going to pull up this window so you can see these a little bit easier. So you see here that aside from these S01 and 2 markers, we have these markers that have these chord names in them. And this is to indicate to the game that the chord has changed. These letters are mapped to a list in Unreal Engine that it pulls from. So each one is mapped to a different color inside the engine. When the chord marker comes up that matches that color, the scene changes a bit, and that's how it knows which color you're supposed to be on. So I have those mapped out for this section of the song. Actually, all 3 sections of the song I have this mapped out on. Yeah, so you see section 1, 2, and 3. And now these are the only chords that are in this song, but I have a list of chords for every song that you can play within the 12-tone Western scale. That's C, C sharp, D, D sharp, E, F, G, all of those majors and minors. We didn't really go too far into other chord types such as like Mixolydian and all like, not that, it's maybe if we want to have like a really advanced mode or something, but this is how all this stuff in the game is parsed. It's just a whole bunch of markers. There's probably a better way to do it, but this was the simplest way, especially since we only had one song. But in a sense, I think it can be easy to do with nearly any song, especially if you have MIDI notes, because even though it's only one note, there's a script in Reaper to make a marker for each MIDI note. So you could just, let's say you have like a song, and you have it just play all the notes, just like in metadata. It can just make a little marker for each one, and you can probably have a script to properly name them all too. I went and named all these by hand. But I'm sure that can be automated. That is how the rings, such as the note rings and the chord rings, are generated in Unreal Engine. It reads all of these markers from Reaper and does something with the blueprints and MetaSounds inside Unreal Engine.
The player times inputs to approaching rings. Each ring is quantized to the song's grid, and each input is scored by pitch correctness in the current key. I synchronize gameplay to a silent clock track using Quartz. The clock sets BPM and time signature, and all ring spawns are scheduled against that grid. The audible music is aligned to that same timeline so visuals remain stable, even if the track swaps. Each song segment embeds note metadata exported from Reaper. I parse that data at runtime and expose the current key and expected note. Player inputs are mapped to 8 notes per key via a data table. When a ring spawns, it carries its expected pitch. On input, I compare the player's mapped notes against the expected note and the quantized window. Correct timing plus correct pitch yields full score. Close timing or near note earns partial credit. Rings color encode the current key. The avatar animates differently on success versus near miss. This keeps the musical state legible without reading UI. If the track modulates or the tempo changes, the system realigns the grid and remaps expected notes immediately. Missed inputs degrade the combo but keep the player in time, so rhythm never collapses. All ring spawns are scheduled, not polled, and audio and UI use the same timeline, so visuals, inputs, and sound remain deterministic across machines. And that's how Project EQ merges rhythm mechanics with musical theory and a deterministic timing model. It rewards timing, harmony, and player expression, and the system scales to any key or tempo. Finally, we'll explore Parallax Protocol, a multiplayer detective game where I implemented reactive sound design using pitch-based progression systems tied to clue discovery. While subtle, these audio systems reinforce player logic and memory through procedural pitch scaling and feedback. Let's take a look at the hacking minigame for the analyst player. It's a simple system that uses Wwise RTPCs to post the correct sound effect sequentially when the player connects the dots from 1 to the max number of dots the current minigame has. Starting in Wwise, the sound effect we are using has a starting pitch voice of -48,000 semitones. To test the limits of Wwise's pitch system, we opted to use the full range of the sound effects capabilities. We hooked up an RTPC called Hack Minigame and set the default value to 0 and the max value to 25, then created the curve to simulate blue notes to the key of the song. The idea is, of course, to utilize the event continuously as soon as the player places the cursor over each note of the minigame, progressively increasing the pitch of the sound effect until the end of the minigame, or until the player messes up and resets the sequence back to 0. Each example in this reel highlights my approach to designing systems that don't just respond to players, they engage with them in real time, transforming how the game sounds depending on how it's played.